yesterday we used the term imaginary, and complex numbers are made up of real and imaginary parts. When you think of the word complex, what do you think of? Complex. Complicated. Complicated. What else? Nothing else comes to mind for complex? Doesn't something that's really complex have maybe several parts to it? You have to do multiple parts. You have to look at the first part, the second part. There are many steps along the way. So a complex number here, what we're going to see, is that it involves a real and an imaginary portion. And we're going to simply look at the four operations with complex. Okay, so first, the definition of this. The set of complex numbers, again, includes the subset of real and imaginary numbers. Real and imaginary numbers. And if you recall, we looked at, earlier in the year all of our sets of numbers, and we said, well, we have our real numbers, and then we have our imaginary numbers. Well, imaginary numbers really have real parts to them as well. And we're going to see what the standard form of that is and how to utilize that concept. So this is called standard form. So A and B are actually real numbers. And A is called the real part, and B is called the imaginary part. And remember yesterday I alluded to several applications of imaginary numbers and where you would see this in technology and science and math. Part of the importance is actually the values of A and B. And believe it or not, when you perform some operations, the result of those operations, I'm trying to simplify it, the whole concept. The results of those operations give you some values which involve A and B. And based on the values of A and B, you could tell if a system is either over-damped or under-damped or perfectly damped. And what dampening is like, how do I describe dampening? You hit a speed bump in your car. Does your car continue to oscillate forever? Does it do this forever? What happens? You hit the speed bump, and then what happens? Right? It teeters off. It kind of stops, right? It flattens out. That's called dampening. And a system that's overly damped, you would hit the bump, and it would stop real quick, like too fast. You would feel a lot of jolt, but it would not vibrate at all. A system that's underdamped, you ever see those movies where like somebody comes up in like hydraulics in the car, and the car is just like bouncing as the car goes up, right? We've all seen something that has that, right? That would be underdamped, because the car, literally, the oscillations continue forever. They're not damped at all. And then perfectly damped would be what your cars really are in general, or what cars today are. You hit a speed bump, and it does this. And you don't really notice too much. I mean, you notice the speed bump, obviously, but you don't notice those vibrations too much. It's perfectly damped. It's a system that does not really cause net external forces on our body. Well, the idea of A and B, the real part A, the imaginary part B, actually affects the outcome of the system. So when you're working with these kinds of mechanisms, I guess would be the term in engineering, mechanisms, whatever you want to use, or apparatuses, and you have to analyze the stability of a system, you're going to end up with imaginary answers as part of your mathematical component, and identifying A and B is actually extremely important in that process. So your book is going to hound you on the standard form, A plus BI, and I'm going to talk about that as well. But the reason for it, okay, again, we're not going to really see the application too much in class. What I would try to do is maybe bring in some example work from grad school, from engineering, to show you guys of where this was utilized. I can do that for sure, but we're not going to actually go through any math involving, dampening of systems or feedback controls of airplanes like I was talking about yesterday. But the idea of A and B being the real and the imaginary parts, respectively. So in the first example, all we're going to do is operations with imaginary numbers. Now, if you saw this, you should not treat it any differently as if I was just a variable at this point. Okay? For the rest of the day, you're going to treat I like a variable, except when you get I squared, because we know that I squared is -1. Okay, so keep that in mind. But here, all you're doing is adding and subtracting. So literally combine like terms. Okay, literally just combine like terms. So in the first one, I've got a 2 plus a 3. That gives me a 5. And then I've got a 4i and a -5i, which gives me a -1i. Okay, that's all part A is, obviously. We're just combining like terms. Part B, I've got 6 minus 2. That gives me 4. And I've got -7i minus a -4i. So -7i plus 4i is negative 3I. Okay, that's all we have for A and B. Again, just combine like terms. There's really no need for you to do this problem, but just to make sure that you guys understand that when adding and subtracting, treat I as if it's just simply a variable. Okay, can we move on to the next one? Combine like terms, we're good on that? Then we're going to start multiplying. So go ahead and multiply the first one out, please. Go ahead and multiply the first one out. When you multiply it out, obviously think about what you have to do. Think about your 4 steps you need to perform. There it goes. So you're going to have, when you FOIL, the terms in the middle that are common. But what else do you notice right away? Always going to be an I squared. We got? Yeah, at the end, you could replace the I squared with a negative 1, making that minus 6 times negative 1, or a positive 6 at the end there. Whenever you see an I squared, get rid of it and switch the sign. Because I squared is negative 1. Whenever you see an I squared, get rid of it and switch the sign it's attached to. The middle terms combine. The middle terms give me a negative I in the middle there. Then I've got 12 plus 6 gives me 18. So I have 18 minus I. And it's written as you see in A plus BI form, where A is 18 and B is really negative 1. Okay, A is 18 and B is negative 1. Again, recognize that these middle terms are like terms and they lead to that simple I right there. Part B, what are you going to do? Same thing, but make sure that you expand this. Okay, don't just square both terms there, please. Think about part B as 3 minus 5i, 3 minus 5i. And go on to part C when you're done and try to come up with a corollary. Yeah, it's 3 minus 5i. Okay, part B, check your answer, please. All you're doing is FOILing here. And the only thing you have to remember is that I squared is a negative 1. Aside from that last fact, this is the same as just simply FOILing earlier in the year. So all you're doing is multiplying things out. But you remember to replace I squared with negative 1. Part C, take a look at, and then somebody make a statement about part C, please. Take a look at your work for part C. If you need another minute, keep going through part C. Jeff?
You're taking the difference of two squares, just multiplying both options.
Yeah, so what do you notice happens to the middle terms? Yeah, again, the middle terms cancel. We've seen this so many times, right, this year, this concept of difference of squares. When you multiply this out, the middle terms are going to be 10i and negative 10i. They're clearly going to cancel. What else? Look at your final answer. What else can you conclude? What else can you conclude? Look at your final answer. Daniela?
It's a real number.
It's a real number. That's the key here. Your answer is absolutely a real number because the middle terms have the imaginary components and those cancel out. The last term has I squared, which is negative 1. The first term simply has a real part to it. So this becomes, again, 25 plus 10i minus 10i minus 4i squared, which is just 25 plus 4, which is simply 29. So we recognize here that 29, the solution that we get, is indeed a real answer. What does this make me think of? What does this make you think of? Gotta think back. Think back to stuff we've done that this is similar to. What is this similar to that we've already looked at? Nobody recalls? You've seen this before. Okay. It's like difference of two squares, yes, absolutely.
And then with the radicals, how they cancel and one over.
Yeah, so do you remember the term was for that though, or you just, because you're describing it correctly?
Oh, it was like binomial conjugates?
Yes, this is the same as binomial conjugates, where we had 3 plus radical 3, 3 minus radical 3, and as a result, the answer was rational instead of irrational. Well, this answer is real instead of imaginary. This is analogous to binomial conjugates. Binomial conjugates, 3 plus radical 7, 3 minus radical 7. When you multiply those out, the radical went away. And remember, the middle terms canceled, you had a real answer that was rational, actually, not irrational like it started. So here, instead of calling these binomial conjugates, we call these complex conjugates. We call them complex conjugates. Okay, so let's jot down that term, please. Complex conjugates. Complex meaning the real and imaginary portion as opposed to binomial conjugates. Now, remember that no matter what you have, as long as it's in this form, you'll get a real answer. Okay, those are complex conjugates. A plus bi and a minus bi. No matter what you do, if you multiply that out, you will end up with a real solution. Okay, a real solution. All right, let's take a look at how we could extend that. Try not to look ahead at the next slide here. If we had something where we had an imaginary denominator, so yesterday we had this. Remember that concept yesterday? We said, okay, multiply by I over I, so that the denominator is not imaginary, yielding 3i squared and a 5 up top. The I squared is negative, so this becomes 5i over a negative 3, or simply negative 5/3 I. So that's what we did yesterday, right? We multiplied by this value I over I. And we also did that, if you recall, go back and think about this. If we had 2 over root 7, to rationalize that, we multiplied by root 7 over root 7. So those are analogous, right? This technique of rationalization is the same as this technique of making the denominator real. Same exact technique. So we take that idea and extend further with that. If we had this, how did we rationalize it? Think back to the last test, the last material we did. How did we rationalize this expression? What did we multiply by? Alex?
1 minus square root of 5 over 1 minus square root of 5.
Very good. Okay, we did that because this was the binomial conjugate, and the answer we get would be rational in the denominator. So what do you expect to happen next? Where am I leading with this? Predict. Chandler?
The denominator would be a real number.
Yeah, so let's take a look at an example like this. If we had 2 plus I, well, how would we get rid of that imaginary portion? We want to make the denominator, again, a real number. So multiply this out by the complex conjugate, and the same thing will occur. Okay, so the same technique we used for binomial conjugates and rationalization will continue to occur for imaginary numbers. They are parallel to one another, these ideas. Okay, so we have a rule on the... Okay, the simple rule is the following. When dividing by a complex expression, instead of dividing by it, multiply both the numerator and denominator by that complex conjugate. Example, this first one here, we need to get rid of that imaginary portion in the denominator. So go ahead and multiply by the complex conjugate. We want to get rid of the imaginary portion of the denominator. So go ahead and multiply by the complex conjugate. And make sure you understand which complex conjugate you're multiplying by. Because I've got a numerator and a denominator. I have a question for you. What if I multiplied by 4 plus I by accident instead? What if I multiplied by the complex conjugate of the numerator instead of the denominator? Because I've seen that happen before. Because it's like, oh, there's two of them. Which one should I use?
Your B term would cancel.
Your B term wouldn't cancel? The middle term? On the bottom? Good. But what would you end up with then? You're right. The bottom would not, middle terms would not cancel. You would not get a real bottom. So what would you end up getting, actually? I'm not asking the exact answer, I'm saying in general.
The reciprocal?
Not the reciprocal. Good idea, though, Jay. Well, finish this off and we'll talk about that. Maybe you'll be able to see a little bit clearer. Replace everything you see with I squared with a negative 1. What's that reduced to? What does that reduce to? I don't even need, and let's put it in A plus BI form. So what does it reduce to? 17 over 34. Should be quick math. Come on, Alex.
1/2.
Yeah, 1/2. So this is really just 1/2 minus 1/2 I. Okay, they're both 17 over 34. If I factor out 17, you'll be left with 1 minus I over 2, which is really 1/2 minus 1/2 I. So go back to the question of what if you had made the complex conjugate of the numerator instead? What if you had used 4 plus I instead? What would the result be? I'm not asking the exact answer, I'm saying in general. What kind of result would you get? What would be the difference in the answer? What?
Would still be, would still have I.
Where?
Would still be,
And what about the numerator?
it
It wouldn't. So as a result, if you do 4 plus I and you make a mistake on the test, you'll get a numerator that is real, as opposed to getting a denominator that's real. That's what we wanted. We wanted a denominator that was real. That was the goal. We would get a numerator that's real and a denominator that's imaginary. And as a result, you'd have to say to yourself, oh wait, I didn't get rid of that denominator, it's imaginary. And maybe that would trigger in your head, I need to use the complex conjugate of the denominator always. Okay, so make sure to use the complex conjugate of the denominator the same way that you use the binomial conjugate of the denominator if it was with radicals. Okay, if it involved radicals. This one, what does it mean? What does it mean? Jeff?
Take 1 over 7 minus 2I and make it rational.
Yeah, make it real. Make the denominator real. Remember, it is rational technically, right? It's not irrational. So that's all we're doing here, okay? We're writing it as 1 over 7 minus 2I because of the reciprocal is what we're seeking. And then to get rid of that, or to make the denominator real, we multiply by 7 plus 2I over 7 plus 2I. Whenever you find the reciprocal, the numerator is nice and simple, right? If I wanted to write my final answer in what's called a plus bi form, how would I write it for this one? The last one was easy. It was 1/2 minus 1/2 I. Those reduce. How about this? Does 7 and 53 reduce at all? 7 and 53, do those reduce? Yes or no? No. So what do?
Leave it.
Leave it. You write 7 53rds. Does 2 and 53 reduce? No. What do? Leave it. I write it as 2 53rds. And then there's your I. Remember that your denominator, and we went over this in like chapter 1, beginning of the year. If your denominator is a monomial, and your numerator has many parts, is a polynomial of some sort, binomial, polynomial, whichever, you can always divide that monomial into every term of the numerator. The numerator has 2 terms. It goes there, and it goes there. Okay, so this is an A plus BI form. A plus BI form. Try the last one on your own. This one's going to be tricky. I'll give sure, I will tell you that. If g of x is given by that function, go ahead and find g of 1 plus 3. There's a lot to do, so see how you can do with this one. G of 1 plus 3. Sorry, 1 plus 3i. I said 1 plus 3. Make sure that when you get to that denominator, you think about FOIL. When you get to this point here, think about FOIL, make sure. put it in, I just got it for you. Okay, so I want to see where you went. There you go. Good. Yes, well, because remember, this is really positive, so 1 times negative, so which would be that a negative right there. And that's a negative. And that negative, double negative next to the positive there. So that's plus or minus there. I'm not sure which one it is. It's a minus, right? Negative 12, and negative 15, which would be negative 27. Try to squeeze it all in there so you can see the process. Most of you did well, but there were little mistakes here and there. I corrected them, but go up until this point and check from here on. And then negative 5 plus 12 by. So be sure to check here. A lot of you got to this answer in the end. Just be careful. So a problem like this, there's so much room for error. I mean, make a mistake with a negative sign in one spot in the beginning and your answer is totally off, not even close. So please be meticulous with your work. Don't forget about this plus 1 that's right here, a lot of you forgot about. Others, when you had an I squared, make sure you switch the sign, obviously. This negative becomes positive, and this negative here became positive as well. Okay, besides that, this is just practice. So it's not a tough technique what we're doing today. You're going to learn more about operations with complex numbers probably next year and the year after, but in the next chapter specifically, we're going to start chapter 7, and tomorrow we're going to start talking about the idea of solving quadratics that have answers that are imaginary themselves. Okay, remember how with quadratics so far we've just factored them, and then we made like a little T-chart and found the 2 solutions. We've done things that always factor. We're going to see what happens when it doesn't factor something. Okay, that's it for this lesson. You can start the homework if you want. I think you have a couple minutes still. Yeah, you have about almost 10 minutes. Definitely get a head start. If you have ask me, call me over, I'll come by and take a look. Okay, there's your homework on the board there. You can take a look at it.